here on time after the conference dinner, especially for Miguel. But let's try to enjoy the last day of the conference. So we will start with Miguel giving a review talk on string universality and classification of string vacua, and then we will have a discussion session about the same topic, another one about non-geometric and non-supersymmetric strings in the afternoon. So let's start. So Miguel, please, the floor is yours.
All right. Thanks a lot, Alvaro, and to you and the rest of the organizers for putting together such a wonderful workshop. I really had a blast. But indeed, as you were saying, it's very, very tough a day like today, you know, December 1st, 2023, right? And it's a very gray, gloomy, rainy morning. You know, when I wrote the slides, I actually took a chance because it might be good weather, but of course the chances, right? So let's picture the following. Picture is like a day like today, you wake up, you're tired. You're very, very tired. I mean, you were partying so hard last night after the conference dinner. We went to this club with all the music. So it's too much fun and drinks, and so there's just no way, right? You're not shape to do anything. And the prospect of the commute to Saclay does not make things more appealing, precisely, to you. Okay. So then you start entertaining the thought. It's like, you know, first talk is review talk, right? It's not like there's no new research stuff. Why not skip it, you know? Just sleep in, then just go to the actual research talks later on. And you close your eyes again, satisfied, smile on your face. Yeah, that's what I'm gonna do. I'm just gonna slip it in. Rest some more, go later. But as you doze off, as you're about to fall asleep, a question floats up to your mind. You know, when one is about to get asleep, like all sorts of random questions can pop up to your mind, right? So this is the question that pops up to your mind. Are we sure, are we really, really sure that we have discovered all possible quantum gravities, even just, you know, even with 32 supercharges, okay? Let's make the game as easy as possible. And even in 10 dimensions, are we sure we got everything there is there? And, you know, the more you think about it, the less sure you are. Right? It's like, how do we know for sure? And if we don't know the answer to that question, you know, it seems like the kind of easiest question one could ask. How could you give the answer to anything else? And then you vaguely remember that the review talk is about string universality. So maybe the speaker will cover this, or if he doesn't, then you can ask. Maybe somebody else knows. And so with a deep, deep sigh, you get up and you get on your way. So if this is your personal story this morning, I thank you for being here. And indeed, this is one of the questions that I'm going to address. It's actually the first question I'm going to address. And I'm going to address a bunch of questions, all centered around the idea of string universality, which is also known sometimes as, you know, string lamppost principle. Somebody was saying that it will be now pretty fun, like the announcement that Jim had in his talk, like the lamp is not working. That would be pretty, yeah, it would be more fun in my talk, I think. Yeah. Anyway, so what is string universality? String universality is just the idea that every consistent quantum gravity, okay, it's a vacuum of some string theory, compactification, okay? As, for instance, you know, people who wouldn't agree with that, for instance, if you believe, like, for instance, look, quantum gravity is completely, you know, it's like its own framework completely separate from string theory, then you don't believe in this kind of thing. And, you know, there's actually a lot of string theory people that sometimes I have trouble communicating this idea because they kind of like have ingrained so strongly that string theory is the only game in town. That is like, what do you mean? Of course it's, but this is a question you can ask. And that question leads you to try and approach the question kind of like from the bottom. I'll try to say, how can I argue? Of course, it's impossible so far to argue it completely generally in every context, but in particular contexts, with more SUSY or in higher dimensions, you might be able to argue, you know, all the possible quantum gravities that are there are actually vacua of string theory. And trying to argue from the bottom up with bottom-up arguments is kind of like what you try to do in the Swampland program. So in a sense, string universality is the end game of the Swampland program. You know, once you establish string theory is the only game in town, then you can just try and construct consistent vacua, and then that's it. Swampland conjectures might still be useful, you know, to guide you, but, you know, as long as you will be doing a string theory vacuum, you will be fine. And so there's been, starting this term was introduced in this paper by Adams, de Wolf, and Taylor. which I will describe briefly later on. But since this paper came up, this paper is a paper about 10 dimensions, about establishing string universality in 10 dimensions. We've been making a little bit of progress. Like not a lot of progress, but it's actually, I think it's quite interesting that we can make some progress in this kind of question. And so that's mostly what I'm going to be reviewing here. So I'm going to discuss what's the status of string universality and a bit of like overview of classification of string vacua. And I will organize the discussion by number of supercharges. So we'll start with 32 supercharges, as I said. Then we'll move to 16 supercharges. 8. What's next? Yes, 4 supercharges. Then 0 supercharges. And then I will just recap a little bit. And for each of the way we organize the discussion is for each of the supercharges, we'll discuss what's the status in 11D. Somehow I jumped 10D, but I also meant 10D, 11D, 9D, 8D, whatever, all the Ds. Okay. So before we get on with it, a very important announcement or thing to say is particularly important the morning after the conference dinner. Okay, I'm a bit asleep. You guys are all asleep. So the way to fight this, okay, is to please interrupt me, okay, at any point with questions, comments, okay. The more lively we make it, the better it is, okay. So at any point, just interrupt. Don't wait until. Yes, excellent, perfect.
Are you talking of the
Sorry.
EFTs?
Very good. That's an excellent question. For 32 supercharges, as you will now see, I will be talking about beyond vacuum, okay, and then. After all, I'm going to be talking about the whole EFT, but just the low energy effective field theory, okay? Ideally, I would like to always talk about the full theory or the whole set of vacua. That's complicated. I can only kind of do that, and with caveats with 32 supercharges. So we'll see now. Because, yeah. Any more questions? Okay, very good. Let's keep it up. Let's start with 32 supercharges, okay? So our quest is, let's assume we have a quantum theory of gravity with 32 supercharges. What can we say universally? Forget for the moment about string theory or anything else. What can we say? Well, with this much supersymmetry, with 32 supercharges, there's just one, if you want to have an Einsteinian theory, there's just one multiplet, right? There's just one multiplet that contains the graviton. And so if you don't want higher spin fields, you're forced to have just the gravity multiplet, and then the interactions are completely fixed by consistency. So the low energy effective field theory is completely fixed for you. There's nothing to do. And you can classify them by dimension. And for instance, if you're in 10-dimensional dimensions, you get to the type 2A supergravity, type 2B supergravity, type 1, right? And all of these have, you could write down a low energy effective field theory which doesn't have a UV completion. That's the whole point of the Schumann plan. But in this case, we believe all of these they have UV completions. So you're essentially done. You have the whole picture. It's just usual M theory star. And if you ask what happens in less than 10 dimensions, you classify the supergravities. They're all dimensional reaction of these guys, which of course you can get from any of these, and they're actually equivalent by dualities. So at the level of massless fields, you're done. There's nothing interesting to say, I would say. Indeed, yes? Yes, very good, excellent question. Yes, I meant that. I meant the two-derivative expansion, and I just meant the low energy. Of course, for instance, this would be a good question of how many possible sets of high derivative terms can I have, okay? And I actually was cheating a little bit. You will see in a couple slides that this is not the complete picture. There's one thing that escapes this description, but I will come up in a couple slides. This is more or less what Jaco was pointing out, like at the level of just two derivative action, the massless fields, everything is completely determined. But the level of high derivative terms, or what's the spectrum of massive states, things are not obviously completely determined. So in particular, you could have a picture like this, where let's say this is like the M theory star was drawn before, and it's actually just like a projection of the way the real deal is. There could be more than one theory which has the same low energy limit, okay? So you could have two different theories that at low energies are type 2B supergravity, okay? You can present that as an abstract thing that could happen, and then there's not much you can say. A way to make this question a bit more concrete and in some sense have a handle at this from the effective field theory, it's the arena of discrete theta angles. So what are discrete theta angles? Well, you know what a theta angle is. This is an example of a theta angle. And, typically when these couplings arise in supergravity or string theory, this parameter theta is actually the web of an axiom. It's part of the lower energy supergravity that I just said was fully determined by supersymmetry. But there are versions of topological couplings like this, where the theta angle is something discrete. It couples to some charge that you don't see at the level of the two-derivative action. And then when that happens, then there's the question of, can I switch it on and off? Is the physics different if I switch it on and off? And so you could have more than one quantum gravity even with 32 supercharges. So for instance, this possibility arises in the concept of type 2B, which we pointed out in this paper. It also arises in M theory. If you want to go examples of 4 dimensions, also arises in the concept of Calabi-Yau compactifications. And for instance, perhaps the clearest, I think, just to give you the idea, I think the clearest example of a discrete theta angle was proposed by Sav in 2013, which is take type 1 string theory. So it has O9s and 32 D9 branes. And because of the orientation, you're projecting out some Ramon-Ramon fields. In particular, you project out the Ramon-Ramon axiom, the C0. So the C0, so you get C0 goes to minus C0. And so if you ask, what are the fixed points? So you say Z0 equals to minus Z0. Oh, sorry. This is the equation you need to solve. I'm not going to risk doing that again, so I'm just going to enumerate the solutions. Right? What's one solution to this? C0 equals 0, right? But because C0 is a periodic variable, also C0 equals pi as a solution. So that looks like a discrete theta angle. Now that discrete theta angle, actually, you can understand that it's a bit like what happens in QCD with massless quarks. It's actually unphysical. It doesn't give you a new vacuum. But there are other cases where you do get new vacuum. Okay, so there's a whole question of classifying these theta angles. And so, for instance, the theta angles are very efficiently classified by something. Yes?
Sorry, but the example you're mentioning is in type 1 string theory, so it doesn't have 32.
That's right. Yeah, that's right.
So you need something like this with 32.
Yes, yes. So, for instance, in M theory, you can do it. Or as I was going to tell you, these theta angles are classified by some Bordessian groups, which I will explain what they are a bit more later. If you can compute the Bordessian group in d dimensions for your quantum gravity, it gives you a list of potential theta angles. So for instance, we computed the Bordessian group for type 2b in Z2 to the 4th. In 10 dimensions, for instance, all of the theories that I was describing here, they have a potential theta angle which is not understood yet, which has to do with exotic spheres. Okay? I can explain a bit more about that later, maybe, or in the coffee break, which is not the main point. The point is, yes, they actually exist. They're there, and we don't know if they are there or not. Do they give you the same physics or not? Okay. They will come up again with 16 supercharges. Well, they just did, but more. Okay. Yeah, it can happen with any number of supercharges. So, even with 32 supercharges, we don't have the whole picture. Another way this can happen, which was mostly discussed on Wednesday, is just, like the spectrum. We were having whole discussions about the spectrum of massive states. For instance, things like ADS5 crosses 5, which has 32 supercharges. So, for instance, you could ask, what happens if you have ADS5 without DS5? That would be an example of extreme scale separation, which we argued in this paper that might be in the swampland, because if you take the infinite flux limit, you get some sort of global symmetry. But the point that I want to make here is that in general, we don't have a way to control the massive spectrum very rigorously and generally. In some cases, like you saw. Yes?
When you say without the slide, it means that you freeze all the scalars of the H supergram.
Yeah.
On the cosmological constant.
No. You get the scalars of the gauge supergravity. Okay. I just mean that's not the Kaluza. Imagine that's just the effective field theory. The N equals H supergravity in 5 dimensions has an ADS5 vacuum, and that's all you get. There's no Kaluza-Klein modes at all. Okay. So it's like making DS5 artificially like super tiny thing, like Nicola was doing in his talk, right? He was making it like very small, that kind of thing. Yeah. It's in that set of ideas. Sometimes you can argue more rigorously, you can get an understanding from that, but in general, we just don't know about the massive states, okay? And so this question of discrete theta angle is just one, it's like in between what you can kind of ask and analyze within the effective field theory, and it probes into this regime of massive state. So this is something I wanted to highlight. Any more questions about this? Okay. So I am done with theta supercharges, right? Well, not quite. There's, I don't know if, I saw Chris Hall was in the program. I don't know if he's around. Hi, nice to meet you. So there's one more example that you pointed out. So you classify the superalgebras. It turns out that in 6 dimensions, there's this 4,0 and 3,1 6-dimensional superalgebras. Okay, that have 32 supercharges. In 8 dimensions, the minimal multiplet has, it has 8, the spinor has 8 components, so 8 times 4 is 32. And I was restricting to multiplets that just have like graviton and stuff, and say, so why are you talking about? Of course, there's more multiplets. This one, the 4,0 algebra has some multiplet, which is not a gravity multiplet. It has some 4-index tensor with the symmetries of the Riemann tensor. But as Chris pointed out in a series of very interesting papers, when you put this guy in a circle and you reduce it, it becomes 5D maximum supergravity. Okay? So it looks like there might be a decompactification limit of 5D and equals 1 supergravity, and for some theories, where this thing is just like any other theory of gravity. Okay? So that's a very interesting possibility. Is this in the landscape or is it in the swampland? This is something that we are looking with my student Michelangelo. Try to understand this construction in terms of swampland constraints, but it's just like a very interesting corner of the landscape of theta supercharged, which is not usually discussed. I just thought I would bring it up. It's super interesting. Yes?
Since you mentioned this, what about these two-star these supergravities? How do you know for sure they don't have?
I'm not familiar with this.
No, I mean these are non-unitary. Maybe, but well, suggested that maybe they can live inside string-sized bubbles.
Well, non-unitary sounds bad, but I don't really know. I'm actually not familiar with this. Thanks for bringing it up. Yeah, like I'll ask you more about it. Yeah. Any more questions? No? Okay. So, yeah. Right, but you can ask things like, does it have a global symmetry?
Right, but I mean, from my understanding, this is theory.
No, in 6 dimensions, right, in 6 dimensions it's very much not Einstein, but when you put it on a circle, right, it gives you an Einstein theory, okay?
It's only a linearized theory, you don't have any interaction.
Yes. So there's more things you could ask about it, right? Like that. But at the level of the multiples at least. I agree that to get the interactions here, because in 6 dimensions, for instance, there's no scale, there's no obvious way to generate that. You have the multiplets, maybe they're generated in some way by some sort of like, I'm waving my hands. You could try to ask, okay, suppose that happens. Can you still say something about it? Yeah. More questions? Okay, it's good because I'm not going great in time. Well, no, actually, no, please ask questions. Please ask as many. It's as good as, it's very good. Okay, so we're not so good at showing uniqueness of string theory, including massive states, even with 32 supercharges. That's okay, that's a very hard question. But for the rest of the talk, I'm gonna make my life easier. This is going back to the point that David was making. So up to now, I was talking about the full theory. Now I'm gonna lower my threshold. I'm just gonna ask. Okay, what I'm going to call string universality for the rest of the talk is, I'm just going to focus on the long-range effective field theory at 2 derivatives. Yes?
So if you restrict like 32
Yes.
But like
yes.
Can you say anything more?
Well, so now there's one, you remember how I gave you for instance, in type 2B in 10 dimensions, that I gave you these 4 possible theta angles? there's a couple we actually, in this tutorial paper, we ruled out because they are, by dualities, you can map them to things that are not there, okay? So yes, so sometimes you can make progress here, okay? And the set theta angle, even though it was 16 supercharges, there's also arguments you can give to show that it's equivalent to the others, okay? So that's, yes, for some of these theta angles, we do not know. For some others, we do know. It's a question where you can actually make progress. Yes, okay.
How much do you rely on the fact that the two theories should have an action?
Well, very much, but you're in 32 supercharges, so it's kind of like almost guaranteed. You know, like the long-range interactions are given to you by just the interactions of, you know, it's like an Einstein theory. With 32 supercharges, the interactions are completely fixed by supersymmetry, and turns out there's interactions you can write in terms of a Lagrangian.
No, I think there's an example. If I'm not mistaken, by Paul Howe, there's a theory in 10 dimensions with 32 supercharges. If I remember correctly.
Oh, okay. This is good because these are theories that I'm really not familiar with. So that's awesome because you're expanding my knowledge here. It might be, yeah. I ask you more about this. Yes. Yeah.
You want to consider so in 10D there it's not only the theta angle, but sometimes if you find a discrete type of anomaly, and I will talk about that in my talk, then there's different ways to cancel. So it's not the bona fide theta angle that Miguel mentioned that appears in this coordinate group, but it's also it's very similar to that. That's another ambiguity.
Yeah, there's things that look like theta angles, but they're related to anomalies, and then you can fix them with anomalies. And then they don't. This calculation of the Bordism can automatically like shift to that. That's a question by Carlo. Yes. Okay, Carlo first, Timo after.
Do we know that those gaugings don't realize?
No, I for one don't know. Maybe somebody knows, but I don't think so. No, not obviously. Yeah. Yeah, that goes to the question of string universality. And that it's a good moment to make a caveat here that most of the progress that I was advertising was in Minkowski. Okay, I'm gonna focus on Minkowski. For 8 and 9 dimensions, that makes sense because there's no ADS, but in 7 dimensions, you can ask that question again, and then I have partial answer. Maybe ask that again. Timo? Okay, good. So, it's not so good. So for the rest of the talk, I am just gonna take a different perspective, which is like, fine, I'm just gonna ask, given a given low energy effective field theory, is it in the landscape? Can I find some string theory which has that as the low energy limit? Yes or no? Okay, and that's what I'm gonna be calling string universality. So the picture is a bit like this. So suppose you have some principles, swampland, anomalies, what you have it, that make all the theories outside inconsistent. And then the things that you can, the effective field theories you can get from string theory, they do not match. Then you would say string universality has not been achieved here. Here we would say the two things match, string universality has been achieved. Okay? Is that picture clear of what I mean by string universality? Awesome. So now let's go to a case where this is actually a bit more interesting. Consistency principles, you know, as anomalies, causality, unitarity. I will use swampland stuff, but mostly the stuff that I will be using is just variants of the no global symmetries conjecture, which is like the best established, strongest conjecture. Okay, so let's just see a concrete example of this idea of string universality. And to do that, this is the arena where we're going to spend, I think, most of the time. We're going to go talk about theories with 16 supercharges. 16 supercharges are great because they're almost as simple as 32 supercharges, but it has enough richness. The life is still quite simple. With 32 supercharges, we only had the gravity multiplet. We now have the gravity and vector multiplets. So gravity multiplet has the bosonic fields are the metrics and vectors, some B field, scalar, and the vector multiplets have a vector and some scalars. And again, just like with 32 supercharges, the low energy Lagrangian is fully fixed by supersymmetry. It's awesome. So it's completely fixed by supersymmetry, so you just need to specify your field content. Okay, and this is particularly simple in 10 dimensions. Okay, so when you go to 10-dimensional theories, there's actually very strong gauge and gravitational anomalies, and cancellation of those anomalies via the Green-Schwarz mechanism, they force the gauge group completely to be one of these 4 possibilities. E across E8, SO32, U1 to the 496, E8 across U1 to the 248. So you now can see the kind of questions that we like to ask in this idea of string universality. These two guys, you know they're the low energy limit of periodic string theories. These two guys, you may have read about them if you read Green-Schwarz with them because they go through this argument, but then they say, there's no string theory that has this as the low energy limit. So that's our string universality question. Can we argue that these 2 points are inconsistent, or can we find some new string theory which has that as the low energy limit? And in this particular case, it can actually be shown that these guys are inconsistent. So the paper that kickstarted gave the name of string universality by Adams, Wolf, and Taylor, they showed that when you look carefully at the variations, SUSY variations of the Green-Schwarz term, it actually doesn't work with these 2 guys. So it's a combination of anomaly cancellation and supersymmetry that kills this. There's a much later paper by Gary, Hitchell, and Kumrum, which introduced a technique. They recovered this result by a different technique, which turned out to be one of the most powerful tools that you can have here. They were looking at the world volume theory of flow branes. Okay, so they were saying, well, you know, there's a B field in the gravity multiplet. That means it's a string, using here Schwamm-Planck conjecture completeness principle. Completeness just tells you that you have states charged under all possible charges of everything, and this string is supersymmetric. I know a lot about this world volume with anomaly inflow and supersymmetry, and that is enough to place constraints and show that these guys are impossible. Yes? Excellent. No, it doesn't. You're very right. If I was being, when you go to a literature, most of the time they write things like this. If you're being a bit, you could say, rigorous or pedantic, you should write an algebra, because the supergravity only depends on the algebra, right? Indeed, so this doesn't tell you about the global form of the, and in particular, there's, as of now, I don't think there's like a really good Schwamm-Planck argument. This is something that we're thinking with Marcus, as to try to argue from the bottom up, it has to be spin 32 mod Z2 or any of the other possibilities. Yeah, different Z2. Exactly. The possibility is actually realized in string theory is not SO32, it's spin 32 mod the Z2 that projects as the vector on one spinner. Okay? So, no, but it does. It doesn't have, exactly. But this is, yeah. Yes. So that's yeah. But yeah, I just want to emphasize this is a super interesting question, and I will cheat a little bit because 2 slides from now we'll be talking about similar questions in 9 and 8 dimensions. But it's really a bit out of the purview of the way I was presenting the thing. I was talking about the 2 derivative action. What is the actual form of the gauge group depends on what are the massive states. So it's not really a yeah. Okay, good. Very good. More questions? No more questions? Excellent. Okay, so we got string universality in 10 dimensions. Welcome to 2010. So what's the interesting progress that has happened in the last few years? Well, we try to address this question in less than 10 dimensions, and it gets a lot more interesting because you don't have Green-Schwarz stuff. You don't have such powerful anomalies. And furthermore, the vector multiplet in 10 dimensions doesn't have scalars, but in less than 10 dimensions it does have scalars. So you have a whole moduli space, it's Narayan type. It's parameterized with the scalars in the vector and gravity multiplets. And these scalars, they are charged into the gauge group. So if you go to a generic point in moduli space, the gauge group is broken to some U1. So the generic point, the gauge group is some U1, which is basically to the number of vector multiplets in the gravity multiplet plus vectors in the gravity multiplet plus number of vector multiplets. And then the only other possible thing that can ever happen in this moduli space is that symmetry enhancement can happen at special points in moduli space. Like you can enhance to SO32 or E8 or whatever. So understanding what's the, what to achieve, what's string universality, what's the thing that we need to do here, we just, since the supergravity is fully specified by the rank of the gauge group and the choices of Lie algebras for enhancement at special points in moduli space, the only thing that we need to do is to classify all possible values of the rank, rank is the number of vector multiplets in the theory, and give you a list of Lie algebras at special points in moduli space. And if you can argue that all the consistent lists match with what you get in string theory, then you achieve string universality. So let me take this, divide this question into 2 pieces. I'm going to first talk about the rank. Just the simple question, how many vector multiplets am I allowed to have? Okay. If you write the low energy supergravity, there's nothing wrong with writing the supergravity. You can find it in textbooks with R vector multiplets, where R is any number you like, 1, 2, 3, 4. You think a bit harder, there are global anomalies. For instance, in 9 dimensions, you can only do it with an odd number of vector multiplets. But if you turn to swampland considerations, there's much more you can do. So first of all, there was this paper by Huri, Hitchell-King, and Kumrum, where they argue that from studying what happens under T-dualities of these theories, that you can get an upper bound from the rank. Okay, so they assume a version of the distance conjecture that allows them to talk about duality, about T-dualities, and that is enough to give an upper bound which matches what you get in string theory. Then in this paper with Kumrum, we used a combination of the covert distance conjecture, which I will talk about a bit more later. It's just a particular swampland conjecture related to no global symmetries, to restrict the ranks in 9 dimensions and 8 dimensions in this way, just from no global symmetries. Ana Maria pointed there's a typo here. So the same technique gives you R is odd in 7 dimensions, not even, sorry about that. And then it's even in 6 dimensions, I guess. I'm self-consistent when I make mistakes. And I also want to point out here that because of the thing that we were talking about, these discrete theta angles, for some values of R, there's more than one connected component in moduli space. So these theta angles that we were saying in 10 dimensions or something, some physical, in 9 dimensions, for instance, we studied in a paper with Hector, they can be physical and they can give you new components in moduli space. And I think that in the story of the rank, the most interesting thing that has happened recently is this paper. This paper is by Bernardo Freiman and Hector Parra, where they identified some rank reduction map. And I guess they can tell you more about it than I can. It's like some sort of bottom-up construction, which recovers all the things that you should recover before. And if you apply to 6 dimensions, it predicts 47 components of the moduli space with different values of the rank, of which 30 of them seem to be new. Okay? This is super interesting. So 6 dimensions, this kind of question is like a very neat arena to work on, I think, right now, because there's like this proposal, following some rules that work, that make sense. They predict 30 new components in 6 dimensions, which we don't know how to construct in string theory. Some of them might be related to discrete theta angles, some of those might be something else. So there's actually very interesting stuff. Great question. So I'm gonna answer that now, because all of this information is not very clearly presented in this list of things. I took an embarrassingly long amount of time to do this in the keynote, so we're gonna spend some time on this slide. So this is all the information that we had before is codified in this table. So you have here the dimension 9, 8, 7, 6, 5, 4. And then the possible values of the rank. Remember, rank is number of vector multiplets, okay? So this black region here that I just dashed out is your bound of 26 minus d on the rank. Then the color code is green if there is an explicit string construction. For instance, we have explicit string construction of rank 1 in 9 dimensions. Red if it's forbidden by the constraints I gave you in the previous slide. And that's red. So for instance, you can see in particular in 9 and 8 dimensions, everything is either green or red. So we can say we have achieved, in the question of the rank, we have achieved string universality. All the values of the rank that we believe are consistent with Sandland principles precisely match what you get from string compactifications. We haven't achieved it in 7 dimensions. So in 7 dimensions, you have yellow stuff. Yellow stuff is unknown. We don't know if there's a string embedding or not. There's no obvious inconsistency, but there's also no string construction either. And, to address Huri's question, in 6 dimensions, I also call it orange, is like unknown. There's no string embedding, but it's one of the ranks in the Hector and Bernardo list. And so, for instance, for low values of the rank, they predict even and odd. Please.
So in 5 dimensions, then saying that an island of Graham-Harvey is not consistent or something?
Or maybe I just, so. No, so double Graham-Harvey is in 6 dimensions, right?
No, they also can for 5.
They also can, okay, so if they also can for 5, then this table needs to be amended.
They argue that is not consistent. So then maybe.
Very good. So that went in my radar. So, okay. So the string I was familiar with, double Graham-Harvey one was the 6-dimensional one. If yes. Okay. By whom?
I think this was involved.
Ah, okay.
But
This is this paper with Stefan. Okay. I missed that. I looked at the paper, but I missed that part. Okay, well, that would be if it's consistent. I'm gonna bring up your paper later on, so maybe we can talk about it later. But this is a very good point. Thanks. Well, it's just because of this black region keeps growing like this, and we're going to 4 dimensions. I had to fit it in the this region that is excluded here. Okay. Yeah.
The claim is not that the maximum length in 6D is 20.
Yeah, that's the claim. 6D with 16 supercharges. Yes. We do not know a single component moduli space with more rank than this. I know, but it's true. With 16 supercharges. These are 8 supercharges. These are 8 supercharges. Yes. Yeah. Yes. 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 So yes. So this like this. So the question is 9 dimensions or?
You know, at 7, 8.
Yeah, that's probably a misprint. After all the time I spent, yes, that's a misprint. Yeah, it should be the other way. Yes, these 2 are flipped. Yeah, and then it's I think. Okay, this is good. Okay.
Although from your paper with Alec and Newton stuff, you try to classify using the distinct.
Yes.
I mean, in principle, there, if you know they're.
Yes. That's right. But the point is that there we don't really have. I'm going to talk about this next. So let me just that's. So I just wanted to bring up like question that of course came up when doing this. It's like here's another. Is there a string island? So what Hector was calling string islands are theories with 0 multiplets. It's just the 0 vector multiplet. It's just the gravity multiplet. Is there a string island in 4 dimensions? I don't know. That'd be an interesting question. Okay. And as I said, some of the numbers are repeated. For instance, these ones are repeated and possibly more, meaning that they have a version with and without discrete data angle. Okay? So I think this is the state of the art modulo this thing with the, thanks for pointing that out. Okay, so I think that's the state of the art with this thing. So you can say that in 7 and 8, we actually have achieved rank string universality. But there's the whole other picture, oh boy, about non-abelian groups. So the whole other point is like, it's a much more complicated question. There's a whole moduli space, and I need to give you a list of what are the possible non-abelian algebras that appear at which particular points, okay? And so one technique that, for instance, that we use in this paper with Alec and Jutta and Kumrum, which originated in this paper by Jutta and Kumrum, is to use, again, it's a variant of the idea of Gary, Hitchell, and Kumrum, which is to use brain probes. In this case, we use codimension for instantons. They see a moduli space, and the moduli space you can identify with the theory, and so you can read off where the non-abelian enhancements. And using consistency conditions, like the moduli space of the probes has to be compact, which is a version of no-global symmetries for high enough codimension probes. You can actually classify and recover also the non-abelian enhancements in 9 dimensions and 8 dimensions. So you can claim you have full string universality there. In 7 dimensions, we can run the same argument, but we cannot claim that we have full string universality. Simply because we don't know enough about the relevant word volume theories of the brains. Yes? There's a 14 equals to 4 string island. Oh, that's awesome. Because then it's like, it's a checkerboard, right? And this is what you were pointing out. It's like, it looks like, if indeed the 5 equals 1 is wrong, there's maybe a pattern here which is observed but unexplained that the ranks are even odd, right? Yeah, that's right. So this would also mean that the theories that you predict here actually don't have string realization, if there was like such a thing. Yeah. Indeed. Very good. Okay, so this is okay. It's very, you give a review talk and you learn about supergravities, and it's super nice. So I'm gonna ask you more about these guys later. Thank you. Okay, so there's also constraints in the global form of the gauge group. which were done, from just from studies of the topological complex of the dimensional theory, or also using covariance and conjecture, which were actually then checked. There's these amazing papers by Ana Maria, Bernardo, Mariana, Carmen, and Hector, where they just went out and computed all the, in string theory, even the global form of the Gauge group. Like, they have these huge lists with like 300 possible entries, and they computed everything, and they all match with these constraints. I would say that in 7 dimensions, there's not too much. But one thing that I think is quite interesting is the approach that was followed by Bernardo and Hector, which is a systematic classification of frozen singularities. So I thought that, now I'm 40 minutes in and having second thoughts about that, but I thought it was a good idea to stop by at little moments and explain what are the techniques that have been used here and why they're interesting. So for instance, one thing that Bernardo and Hector did, they were classifying what are the possible ways to glue frozen singularities. So what is a frozen singularity? Okay, but this was nonsense. You mean that it was kind of like the rules were implicit, for instance, in triple fluxes and strings and stuff like that, right? Yes. Yes. It took 20 years from the triple fluxes and strings until. Yeah. So what is a frozen singularity? Well, it's the M3 perspective, which is from the GG paper, or one GG paper that I think Hector was talking about, is, you can have, in M theory, you can often have singularities like R4 mod Z2, and this, where you can blow up to a smooth geometry. But one thing that can happen in M theory is you can turn on a non-trivial period of the freeform here, and since this is a smooth space, if you wanted to blow it up like this, then that would mean that just by Stokes' theorem, there would be a non-zero G4 here, which would give you a potential. So just by turning on these discrete periods for the C3, you can actually make this blow-up mode massive. And so you are freezing the singularity. Like, the modes that take you away from the singularity is no longer part of the moduli space. Okay? And so, for instance, you can have M theory in K3, you can have M theory in K3 with frozen singularities, you can do all these things. And this is, I think, a quite interesting idea, and we should study frozen singularities more generally. Like, for instance, if you're doing 3-dimensional compactification in 3 to 3 dimensions, there might be a chance to freeze singularities with integrals of C7. Maybe this is something that has been explored. I was not familiar with it. I haven't seen it in the literature. Maybe somewhere there I just missed it. That's an interesting idea. Another promising idea to classify and to get these theories with 16 supercharges and also Lorentz supercharges is this covariance and conjecture, which is based on the idea that in quantum gravity, if you have non-trivial topologies themselves can give you global charges. So for instance, imagine that I have a constant time slice in, let's say, a 5-dimensional theory of gravity, it's topology R4, and then I glue a K3. Since quantum gravity makes sense in different topologies, this is something I can do. Now, once you do that, it's clear that the topology of this initial time slice cannot change in the small deformations in the smooth GR evolution. So you might say, oh, the topology of the K3 is like a global symmetry, it's a global charge. But since in quantum gravity topology is dynamical, the topology might fluctuate by some non-perturbative process. So here's the most general topological fluctuations you could imagine in gravity. So this is, let's say, Euclidean time. You have some manifold M1. It fluctuates, so, it reconnects in weird ways, gives you some manifold Z2 after that. And in between, there's some manifold C of 1 dimension more, which is describing interpolation. This thing is called a covariism. It's a covariism between M1 and M2. And it's something that has been studied in the math literature, and the set of covariism classes forms a group. So from this argument, you could imagine, you would expect that something like covariism groups would count global symmetries of quantum theories of gravity. Okay? That was a bit quick. Questions about that? Okay, so the basic idea is that the covariance groups just gives you global asymmetries in a quantum theory of gravity, and so it captures, the covariance captures transitions that cannot be killed by smooth transitions, and after you quotient by all of that, there's still something that remains. But since we believe there's no global asymmetries in quantum gravity either, it must be possible to introduce additional defects that can kill things that are not in trivial Bordism class. These things cannot be made to disappear, cannot be made boundaries of smooth manifolds, but they can be, in string theory, it often makes sense in orbifolds and more singular geometries. So what this is telling you is that whenever you have a non-trivial cobordism class, there should be an associated singular defect, which makes it a boundary. There's been a recent great deal of work on cobordism conjecture because it allows you to say strong things about gravity without assuming string theory. So, for instance, this restriction on the periodicity of the rank we got from using cobordism conjecture. You can use it to produce similar constraints in 6 dimensions, although less powerful. And more recently, it has been used to predict new branes. Okay, I think Fabian was mentioning these branes yesterday in the discussion. So whenever you have non-trivial cobordism classes, you can use it to predict new branes, and we've been working in type 2. It's also working Herodic. You predict new non-supersymmetric branes. So Fabian was asking, why don't you do string compactifications with these and try to get like new non-SUSY stuff? You might be able to, but these branes always have gauge charges, so there's always discrete versions of tadpoles that you need to cancel, which makes it a bit complicated. Okay, and just to wrap up a little bit, there's been the discussion with 16 supercharges. There's been a recent source of work with this, and not directly related to the question of string universality. For instance, we have a systematic study of the infinite distance limits and checks of the emergent string conjecture. There's an intriguing paper by Ruben and Lau on a consistency of contour terms in 8 dimensions, which might be leveraged into constraints. There's even like bootstrap studies. There's this paper which assumes a very strong ansatz for the S matrix inspired by string theory, but then they recover the upper bound on the rank of 26 minus D with 16 supercharges. S matrix stuff, like completely related to string theory. And so I think this is a very promising idea to check both landscape and swampland ideas. I think it's a great arena to look into stuff. Okay. Any general questions about 16 supercharges? Yes.
Maybe, can you say anything
About 2, well, right, with the rules of the game that I was giving myself, it's well, 2,0 with the rules of the games I giving myself is kind of fixed because local anomalies, right, in 6 dimensions, they completely fix the theory in the end. So, the level of the supergravity fields is completely fixed. You might ask about theta angles and stuff again, which I was not. There might be a question there, but yeah. All of this in 6 dimensions is 1,1 modulus precisely because of that reason. There's more freedom there. Okay. He asked if for every 2,0 anomaly-free string supergravity is a string relation. I just think it's just one, right? So with 2,0 you describe it into 1,0 language, it completely fixes the number of multiplets, and that's just one, and that's it. And yes, it's like whatever you like. Type 2 on it's like a K3 or something. Yeah. Any more questions? Yes.
You have some expectation on how this analysis change when you include gauging?
Very good. So this is go back to the question of what happens with ADS and so on and so forth. I don't think that's a great question. For instance, in 7 dimensions, that's also very great. I don't think there's papers on this. Like try to understand this analysis for supergravities with ADS. There's not much. One thing I can tell you is, for instance, like the modulo 2 condition on the rank that we derived in 7 dimensions seems to also be true in ADSs. And it's related to the fact that the number of fixed points of involutions of spheres that would give you 17 equals 1 theories is always even. And when I say always, it's always all the cases I checked. Okay.
Independent, because okay, within 7 dimensions where the aging, you don't have a lot of freedom.
Yes, yes. I'm saying start there. Is the most constrained case, is the most interesting. Even there's no systematic studies, there's no papers, I think, particularly describing this from Swampland point of view.
But the aim is to do the analysis dependently on the aging or start focus on a particular age, gravity, like in 4D. And
Whatever you can do, right? Like you could do both. Yeah. Yes.
Isn't there explained non-compact gauge supergravities with non-compact gauge groups are in the swampland?
Yeah.
Which you often hear people work on the swampland saying, but in the big supergravity community.
Okay. Yes, yes. I was kind of like taking this in from the get-go, so I was like automatically excluding anything like that. And so the argument for that is that if you have anything with a non-compact gauge group, okay, which is not spontaneously broken, there's gonna be a global symmetry. And the stupid argument for that is, imagine you have gauge theory in 4 dimensions with R gauge group as opposed to U1. Okay, you have R gauge group, you could have particles with charge 1 and let's say square root of 2, and the square root of 2-ness of a state is a conserved charge. So as a particle with charge square root of 2 can never decay in a finite number of particles with charge 1 or 0. So it's kind of like independently conserved. So that gives you global symmetry.
But it will always be spontaneously broken. The kinetic term is a Kaplan-Schilling metric for the.
Well, so there's 2 things there. If you can go to a point in moduli space where the non-compact subgroup remains unbroken, then you're dead. But if not, you're not. Take SL2Z. The SL2Z of type 2 string theory is non-compact. It's gauge. Yes?
Yeah, I have some more comments on applications. First of all, it's always the case that the symmetry group is spontaneously broken down to a compact subgroup. Secondly, a lot of them typically lift up to 10 or 11 dimensions with non-compact internal space, which means that it is part of the 11-dimensional, 10-dimensional set of solutions, but from a lower dimensional point of view, typically there isn't a mass gap, so it doesn't give you.
Right.
So it's consistent truncation, but you try to include the higher dimensional theory, there's no mass gap.
Right, right. So there are consistent backgrounds of 11 dimensions, 10 dimensions. You wouldn't say they're like compactifications with a finite and Planck sort of thing like that. Yeah.
I think it might also be interesting this audience that you had a paper with Hausen where you realized that they see the solution. Of course, and they see the solution with the non-compact internal space. But
I see. Yeah.
Yeah. So the SO4 common ball gauging in 4 dimensions, for example, has an unstable de Sitter.
I see. It's unstable, and then it goes if you have the extra Cossacane modes or something. Okay, that's super interesting. Yeah.
So even the low energy supergravity.
I see. Yes.
Maybe sorry to interrupt this. It's very interesting, but we have a whole discussion session on the same topic afterwards. Maybe we can try to let Miguel wrap up in 10 minutes, and then we defer on
those 5 minutes you promised yesterday. I'm gonna need them.
Yeah. Let's say they were included in the 10 minutes.
No, it's actually fine, because I really wanted to focus the most on 16 supercharges, because this is where most of the progress on this question of string universal has been made, and because as you're gonna see now, things start to unravel when you go to the supercharges, and it's just what you might expect, right? These kind of questions you can kind of ask in setups where the landscape is actually sort of like a mini landscape. There's just so little parameters that you could, in principle, hope to have like a full classification. This already unravels in just with 8 supercharges. So the highest dimension possible is 6D 1,0. You can have vectors, tensors, and hypermultiplets. And there's many constraints from local anomalies and stuff like brain probes. But there's actually many, in this particular case, there's infinitely many families which remain, which they have they satisfy anomaly cancellation. There's no obvious reason why they would be wrong, and they evade all the constraints put so far. And the situation has been made worse recently by a paper by Gregory Lodges and Yuta Hamada, where they have written down infinitely many infinite families. So it's like double infinite. So it's making our life harder. So you see, it's so big, it's unlikely to be classified without new ideas. Now we're talking about Calabi-Yaos, right? And theory in Calabi threefolds, and this is this world of disease, right? So it seems unlikely to be fully classified without new ideas, but there are some new ideas. So there's I don't know if Marcus will want to talk about this, but this set of ideas, there's stuff in 6 dimensions using quadratic refinements and consistent conditions of those, which might give you additional constraints. And there's also this interesting paper by Huri and Kunrun, where they argue that by studying the frame pros, like stuff like, at least, infinitely many massless modes in the swampland. So I wanted to highlight a bit more constructive methods, because it's talk about string universality and classification of string Bacchia. I don't have a lot of time, so I will just highlight them very quickly. So how do we get 6D 1,0 Bacchia? What are the canonical ways? Heroic or F-theory? And something that is common to both of them, it's technically part of both of them, but it's also different, is asymmetric orbitals. There's a lot of stuff to be done with asymmetric orbitals. We just haven't it's okay. I just haven't fully classified them. And I don't know who you're going to be talking about this. Well, then I'm not going to say anything. So, for instance, if they find stuff which is not what you would get here in a geometric theory corner, right? So that's super interesting. So I know it's like you can get the complaints that this is all stuff from the 90s or the 80s, but the whole point is that the landscape is so vast that even with all the work that was done by many of you guys, there's still many things which have been not discovered. And here's an interesting question that I really wanted to pose, which is, asymmetric orbitals are great, they give you new components, but I only know how to do orbitals if you have a perturbative string worksheet. If you go to tau equals I in type 2 in 10 dimensions, and you ask me to orbifold by the Z4 symmetry that appears there, I don't know how to do it, okay? There's one paper that I know that tries to say stuff about this, which is by Yakari and Volpato, which I think is super interesting. It's just something we should all think more about. One other way to, if you want to do orbifolds, perhaps even away from the worksheet, but you're scared, you don't know how to do them, why not try to do free orbifolds, which is like a bit of a misnomer, an oxymoron. You can quotient by stuff, but which doesn't have fixed points. So there's no twisted sectors, you're good. And so, for instance, you could try and do quotients of Riemann flat manifolds. And this is a super interesting arena. I think Peng is going to talk about that too. You can get whatever. You can get a Calabi-Yau like this. You can break supersymmetry, and you can include duality twists, which is the paper we were mentioning before by Chris Hall. This super interesting paper. They're studying T-dualities, like twists. You compactify a torus and then the quotient by a T-duality twist. But why not do it more generally? Do the full U-duality, right? It's super interesting stuff, I think. I think this is a great arena to make more progress. And it's part of a bigger story, which I will not discuss. For instance, there's double field theory, general geometry, new manifolds. And, there's a lot you can do here, which is difficult in other setups. For instance, yesterday we were having the questions about getting numerical Calabi-Yau metrics. Here's a paper which gives you the full spectrum of the Laplacian and Néel manifold. So in some of these setups, they can break all the SUSIs and still give you a lot of control. I think we should explore them more. Sort of have generic slide here on general stuff that has been done with heavy supercharges, like I'm trying to understand towers of states and interior of the moduli space, which I'm going to go pretty quickly over it. Construction of numerical metrics. There's an interesting relationship between the curvature of the moduli space and decoupling. But even the basic question of, is the number of Calabi-Yau threefolds finite? It's not answered, right? And one toy question which you could ask, which I think is quite interesting, it's just like, as a target, try to understand if just 5D equals 1 pure supergravity with no vectors, no hypermultiplets. It's like a particularly simple, particularly nice, effectively theory one can write down. Could this be in the landscape or in the swampland? That's an interesting question. For supercharges, I said there was a lot of discussion on Wednesday and Thursday, so I'm going to be brief. And in fact, I'm going to be so brief, I'm kind of like going to skip it. So actually, I'm referring to a lot of talks. There's this whole set of ideas on tameness that I wanted to highlight, and general structure of the flux potential. So this maybe can give us, it's certainly a different way of thinking about the structure of the flux potential, which is, we always need good new ideas. We heard a lot about KKLT. There's of course some questions to ask, but there's progress. This progress being made. There's the Sitter-no-go theorems, generalizing the Maldacena-Núñez. And let me get back in my last 3 minutes to what to me is one of the most interesting cases, which is the case where you actually just break supercharges from the get-go. And you can get all sorts of weird stuff. So I made my slides some days ago, and turns out some of my slides are actually rip-offs of talks that have already happened before in the conference. So this is a rip-off of Bruno's talk. So there's lots of weird stuff that can happen with zero supercharges. You can have stuff like scale separation, which is super interesting. You know, all this discussion of scale separation is really a discussion about CFT. So whether we can realize it on the CFT, because otherwise it's just there on the face. And then there's remarkably simple ideas for the Sitter constructions. So Bruno told us all the progress about trying to get like explicit examples with numbers and metrics. But I think this idea of using Casimir energies to get the Sitter. So again, super interesting. It's not what we do usually. It's just like I think a new idea. We were talking about classification of string vacuum. When you go away for system supercharges, it's really classification of lampposts. It's Calabi-Yau lamppost or the F-theory lamppost. There's many more things that you could do. Just wanted to highlight a couple of those. For instance, here, this idea is the manifold doesn't, can be hyperbolic. It's a very nice idea, but you could try to combine it with, let's say, the Riemann flat guys from before or something else. It's an interesting area also for non-SUSY strings. We have some talks later on, I think, discussion. So I'm getting like a bit of a summary from this workshop. This Youngsters workshop was organized by people in the audience just last week. It was an online workshop, very fun. So for instance, we learned that we can now do closed string tachyon condensation for some of the non-supersymmetric strings. And if you do it in a certain way, the endpoint of that is the near horizon geometry of other branes in the SUSY strings, which is so cool. It's like, oh, this non-SUSY tachyon condensation actually goes back to the SUSY strings that we know and love. We actually have a recent classification of the non-SUSY erotic strings. We now know there's not more than what has been constructed so far. We do not have a similar thing for open string models, but there's new constructions by Emilian and friends. And as Severin mentioned yesterday, systematic exploration of the moduli space of the SO16. So there's a lot of things that are happening there. We also show, I forgot to include the reference, but this is a paper by myself, Matilda, Ivano, and Arun. Nobody had checked that the 10D strings were free of global anomalies. We did the correlation calculation. We checked they're free of global anomalies. And there's constructions of AD3 back as well. You might ask about the stability. And then this is actually my last, second to last slide, which was essentially also in Severin's talk. So I'm just going to quickly. It might seem that non-SUSY strings are great to try and get the Sitter because they get a positive potential, which on the face violates one of the assumptions of Maldacena-Núñez theorem. However, there's many extensions of these theorems applying to non-SUSY strings. You know how Maldacena-Núñez can also be extended to apply to massive type 2A, even though it also has a positive potential. One intuitive way that I have to understand at least the extensions of these theorems to the open string models is the open string models, they always have corners in their moduli space when you put it on a circle, which are dual to massive type 2A with orientifals. So it's not that different from massive type 2A to orientifals. For the hydraulic, it also works. There's, for instance, this paper by Ivano and Stefano. They also do it for the SO16 and SO16, and that one is just like a general linear thing. Anyway, somehow I managed to finish roughly on time. To sum up, and this is a summary which is mostly for the younger people, to the PhD students or master students maybe. At some point, you're going to go to a party, and you're going to run into this guy or someone equivalent, and they're going to be, oh, so you're doing string theory, but hasn't string theory been proven wrong already? You've been at it for 40 years, and when are you going to give up, right? So if you run into this person, you now know what to tell them. The landscape is so vast. 40 years are not enough. We actually need more people, not less people, to explore all the corners. A lot of the core ideas that I told you about, essentially, I would even say all of the ideas I told you about here, they're old. The core ideas are from the 80s and 90s. It's just that they haven't been fully explored, and there's so much more that we need to do. And so maybe I can convince this guy to join us and help explore the landscape. Thanks so much.
All right, so thank you, Miguel, for the very nice talk. And we already had a lot of questions, but maybe we have time for a couple of quick questions. I see one over there. There, Thomas.
You started the talk with many superchargers and in high dimensions, and you mentioned I will study Minkowski, and then suddenly we went to lower dimensions and to less supersymmetry. So I was just curious to know, is there a clean statement about the possibility of quantum gravity with Minkowski with 4 or less supercharges? Is there a known statement?
No, I don't think there's a known statement, right? Like,
do we believe there are Minkowski vacua with 4 supercharges or less?
Well, there's going to be a question. You mean completely stable? Right? So that when you get Minkowski, it seems like a bit of a fine tuning, right? Because if you have 4 n equals 1, then naively you would expect, if it's SUSY, it's going to land into ADS, right? And without it, it's going to be, it's going to be very difficult, right? So from the point of view, I think the bottom line is that string theory is actually a natural theory. It doesn't really do unnatural stuff most of the time. So when you want to find like very little numbers, as in Jacob's talk, you really need to work hard, right? So, there's not a theorem that might not be Minkowski, but there's also not like it seems very difficult. It sounds like infinite fine tuning, right?
If you compactify F3 on a 4-fold that doesn't have any rigid divisors, you have no fluxes either. Like, where does the superpotential then come from? Couldn't there be just one that doesn't have a superpotential at all and has moduli space?
Yes, yes, it could definitely happen. It could definitely happen, I would say. I don't see why not. Yeah. If it's non-SUSY, well, you're saying it's SUSY, so yeah. Could be. I certainly have no way to exclude it. Yeah. But it would be like super. Even if it's it feels like a bit of maybe like a dumb thing or a 5-page paper. I think that writing such a paper, one can come up with a concrete example, would certainly be nice. Would be helpful. It's like, next time we have this conversation, we'll be like, here's the example.
We have to prove that there's absolutely no instantons.
Yeah, this is why these questions end up being interesting. Right? You start thinking, okay, fine, come on, but then you start thinking how to prove it, to argue actually. I think such a paper would be great because even if one doesn't manage to prove it, it's gonna point exactly to where are the difficulties, what needs to be done, etc., and so on. Where could it fail or whatever. For instance, I think a good strategy there might be with the Riemann flat guys, which is like completely different to what you were saying. But the Riemann flat guys, they often have the inherent properties of the parent torus, which has like n equals 8.
So it would be expected that if you have really exactly vanishing superpotential, you would have some enhancement of supersymmetry.
Yeah, like in the
underlying, like with chi equals 0 or something like that.
Yes.
Because also the rigidity of instanton conditions is too strong. It's just a sufficient condition to have rigid devices for having a superpotential.
I see.
So it would be very surprising if it were really.
I see. Okay, so for instance, you're saying, maybe let us understand that I gave this example here, which is a paper by Volker of Riemann flat, Calabi-Yau 3-fold, this guy. For instance, maybe you're saying if we were to do, F theory on this guy, we get a 60 and equals, well, okay, never mind, 60. So, yeah. But along these lines, yeah.
All right, so if there are no any further urgent questions, we can wait for the discussion session and thank Miguel and all the other participants in the review.
Sorry, I did your time. Don't worry. No worries.
Yeah, I try to. Yeah, give me a 20 minutes warning so that I have 5 minutes to finish the talk. And it means, okay, wait.
All right, so our next speaker is Marcus Diericke, and he's going to be talking about string universality and mixed anomaly. So please, Marcus, the floor is yours.
Thank you very much, and a great thank you to the organizers for putting together this workshop. So since the organizers asked me to be on topic, sort of, I decided to give like a summary of the work I did during the last 3 years or so in the connection with string universality. And of course, I have many collaborators. Many of them are here, so feel free to approach them during the coffee breaks and ask them. Okay, so I list some of the works that I will mention in this talk here on this slide. So let me start by saying what happens if I have a theory that is gravitational and contains a p-form field, right? It's very common for us because we work with supergravity that have these fields naturally. In string theory, they're everywhere, right? Raman fields and so on and so forth. You just have this, this action here, which is a kinetic term, but this action turns out to generate some generalized global symmetries. Right? So if you have a p-form field, you get two global symmetries. You get the electric one, which is just shifting this p-form field by a flat p-form. And you get the magnetic dual symmetry, which is a q-form symmetry, where q is d minus p minus 2, which shifts the magnetic dual as such. But then, of course, there's a problem, because I just told you you're in a gravitational setup. I told you this theory would have global symmetries. And there are no global symmetries in quantum gravity. So if you claim that something like this appears, you better get rid of them until you hit the point of the UV completion. So how do we do that? Well, the natural thing you would do is you would break them, right? And you break them by just coupling your p-form fields to dynamically charged objects. And since they're higher form fields, the electrically charged and magnetically charged objects are generically extended. So for the example I pointed out above, the p-form field would couple in this standard fashion to a p-dimensional object, and the magnetic q-form couples to this q-dimensional object. Right? But you have to be very careful, because you have to include enough of these states in order to break everything. So there is no even discrete subgroup left, which would again lead to global symmetries and would spoil your no global symmetries conjecture. So how do I do that? Well, I also have to be careful in the other direction. If I break them, I shouldn't break too much, because I will end up with a theory that has inconsistencies due to Dirac quantization, right? So imagine I have a magnetic object that I call minimal, that generates in its asymptotic geometry, it generates this magnetic flux on a p+1 sphere, right? So this is the magnetic object. So I draw it as a point, but it can be extended, and it has this sphere around it, which is threaded by this magnetic flux. So now how can I prove, or how can I show that I have to be careful in terms of Dirac quantization? Well, I can take the associated electric object and put it on a p-dimensional submanifold of this asymptotic sphere in such a way, right? And then say, is this configuration consistent? Right? And the answer is, well, it depends on the charge, electric charge of this object, because I can use Stokes' theorem, and I can either fill this electric coupling of this p-dimensional object in the interior, so then I have a picture like this. But I can also use Stokes on the outside, and I do the following thing, and the demand that is consistent means that this gauge invariant quantity has to be single valued. And for a minimal magnetic charge that I normalize in such a way, that would tell me that the electric charge has to be integer. Right? So in particular, if I would now include something that is not integer, I run into a problem. It's just an inconsistent configuration. So whenever you want to get rid of these global symmetries, you have to be careful. Now, this is actually correlated with something that is a large gauge transformation. And the way this is true is just simply how we construct this higher form magnetic fluxes is we take this p+1 dimensional sphere, we cut it in the middle, the equator is a p-dimensional sphere, right, and we glue them together up to a large gauge transformation. So this statement of Dirac quantization is sort of a statement that this electric operator here, this higher dimensional generalization of a Wilson line operator, is invariant under this type of large gauge transformation. Okay, so if it's not, then it points to your theory not being gauge invariant, so you can call it an anomaly in this sense. Okay, so how do I break it correctly? To summarize, right, I have this electric states, I have this magnetic states, and I just should include all as many as possible, but not too many, right? So this is the correct picture. I have this lattice, and I should include all of them I'm allowed to, but I should not have these free columns or rows, because then I would generate like electric or magnetic remnant discrete symmetries. But I should also not include too many of them, because I would violate Dirac quantization. Okay, so that's the general story that we'll work with for the rest of at least of the first part of the talk. Now, the thing is that not only these objects are included, the elementary object are charged, but also other things can be charged, right? So, for example, I can have a gauge sector, which has the standard two-form field strength, which can carry electric charge. So if you have a coupling in your theory of this type, this tells you that this gauge configuration generates an electric charge under the p-form field. The same is true for the tangent bundle. So if I have a coupling of Cp to some combination of the curvature two-form, that means my space-time manifold, if it has curvature or gravitational instanton and the likes, can carry these electric charges. And also if I have other p-form or k-form fields that couple in such a way, right? They will also generate these charges. And all of these configurations need to satisfy the same quantization condition. So I should never have the possibility to generate something that is fractional in order to violate the Dirac quantization. And that's sort of how we get extra constraints, and we can approach some aspect of string universality. So this issue is a little bit subtle, because usually it's related to not only local information of my gauge theory or my gravitational theory, but something that I would call global information, right? So it's something, I have this topological term that usually is integer quantized. So let's take the example of a gauge sector where I have this instanton density trace f squared. And whenever I have a simply connected non-abelian gauge theory, the instantons would be, the instanton numbers are integers. Now, however, if my gauge theory is not simply connected, but you have this for example, SU3 mod Z3 or other situation, then in general it can be fractionally charged, right? So it really depends on this global piece of information. So if it's a pure gauge theory, I would never be able to test it in local scattering experiments, because I have gluons, right? Only, so these are the same local degrees of freedom here as they are here, but it has to do with this global properties of my theory. The same is true with the gravitational side, right? So there I can have gravitational instantons. So because slide is not wide enough, I, instead of trace r squared, I just wrote the first Pontryagin density, right? So this is also typically integer quantized in the correct units, right? But only depending on the type of manifold you consider. So spin manifolds will have a different quantization law than, for example, spin C manifolds or other type of manifolds that you would allow. So again, it depends really on the global structure of your space-time manifold and what kind of the quantization conditions appear here. And of course, this leads to a correlation with the Dirac quantization whenever I now couple my higher form fields to these topological densities. So today I will mainly focus on the gauge sector, but I think there's a lot to be discussed also for the gravitational sector, actually. So now let me give a little bit more explanation on what this global data means. So I already said that if you have a pure non-abelian gauge theory in any dimension, right, your local degrees of freedom are gluons, and there will be the same for all theories that have the same gauge algebra. But we care about the gauge group, not only the algebra. So that means that we care, or we have to focus on this center of my non-abelian group. So SUN, for example, has center Zn, but also spin groups and other groups have a discrete center. Now, if you have a pure non-abelian algebra, then you have a center one-form symmetry. Also, again, a global symmetry that would appear, and of course in quantum gravity, you would not allow global symmetry, so again, you have to get rid of it. And there's two ways here. So you break it, that's the same as we did before, right? We include now dynamical states that are charged under the center. You get rid of the one-form symmetry. For example, in the SUN case, if you have a dynamical degree of freedom in the fundamental, you would break the ZN one-form symmetry completely and you're fine. But you can also gauge it, and by gauging the center symmetry, you go from the simply connected version to the non-simply connected version. But you have to be very careful, because by that you include these fractional instantons that can change your conclusions about Dirac quantization. Right? So that's the argument we're going to run here. And also in this gauged version, of course, you're not supposed to have some representations that are charged under this part of the center that you gauged with. So it really has some restrictions on the spectrum of dynamical fields of your theory. So for example, if you have a theory that has gauge group SU3 times SU3, it can have representations of the form like fundamental times singlet, whereas if you have SU3 times SU3 mod Z3, this cannot happen anymore. So I imply that this Z3 embeds non-trivially in the center of both groups, right? And depending on how you embed it, you either have fundamental, fundamental, or fundamental, anti-fundamental. But this representation could never show up. Of course, there's a subtlety here. Once I do this gauging, I get this quantum symmetry, the dual symmetry on the magnetic side, and I also have to include some magnetic states here. But let me not go into detail. So what are some examples? Well, in 4 dimensions, I can just take like an axion degree of freedom, a periodic scalar field that couples to my instanton density, right, of this type. And there have been some analysis precisely of this mixed anomaly that I want to discuss between now a shift symmetry of the axion and this gauging of the one-form symmetry in the gauge sector here. And in fact, there has been a couple of recent papers where they do precisely this realization in the standard model. And you might be surprised or you might not, depending on whether you've heard about it, that we actually don't know the gauge group of the standard model. We know the gauge algebra, but precisely this global realization, there could be a Z2 discrete factor in the embedding in the center, a Z3 or a Z6. Right? And depending on what it is, actually this coupling will be restricted, and that actually has consequences for axion physics, under some assumption, of course, that there is a single axion, that is the QCD axion, and so on and so forth. Okay? But of course, these couplings are very general. So for example, if you go to 6 dimensions, n equals 1,0, you have a bunch of tensor fields. So you have these 2 forms that couple to the instanton density. Right, and there's much work going on here. But today I will actually focus on the 8-dimensional case, minimal supersymmetric, so 16 supercharges. And the reason is that in this case you have a single 4 form that is in the gravity multiplet that couples now to all the potential gauge sectors you have in this universal way. So you have C4, wedge, some coefficient that I will explain, and then these instanton densities. And that is the reason why in 8 dimensions, because this is the unique term that universally couples, you get the strongest constraints. You can run similar arguments as we did for 6D, but because you have more flexibility, the constraints are not as strong. Okay, so what is the logic here? Well, we start with this term here, right? Then we do a large gauge transformation of the C4. Remember, this is the thing that embeds, or this code encodes the Dirac quantization. And then we better make sure that this thing I get here integrates to an integer, right? And that means because I normalize the instanton density in the appropriate way, and this is also in integer cohomology, that the sum over all these coefficients that appear should be an integer. Then I'm fine. I don't have this mixed anomaly between the global one-form symmetry of the gauge sector and this large gauge transformation of my p-form field. And now, if I, on top of that, include some other restrictions that I can get, for example, from anomaly inflow, and I apologize that I should also include the paper by Huri here. So the consistency conditions in 8 dimensions with n equals 1 supersymmetry tell you that the rank of your gauge group should be smaller or equal than 18. And as we heard from Miguel, by using these anomaly inflows and I-folds that are predicted by the cobordism conjecture, you can also show that R minus 2 is divisible by 8. So this gives 3 possibilities, 18, 10, and 2. So what are these coefficients that need to add up to an integer? Well, if you have a gauge group that is composed out of non-abelian factors with some discrete quotient, again, I embed this in all these simply connected pieces here, then is composed out of three things. Namely, there's a Qi, which is precisely how fractional can my instantons be, right? There is some Ki squared, which is how do I embed my Zn into the different simply connected factors. And then there's some discrete redundancy in the supergravity theory in principle, which is related to integer levels. However, one can show from anomaly inflow arguments that at least in the case of rank 18, all of them have to be set equal to 1. So in rank 18, you don't have this redundancy here. And then you can just run the argument, right? So let's consider we have a rank 18 theory in 8 dimensions, n equals 1 supersymmetry, and it only has SUN gauge algebra vectors. And then you just are faced with a challenge of combining. So the Q's take this form here. And now you have to find a combination such that the rank adds up to 18, and this number is given by an integer. And it turns out to be very, very restrictive. And of course, we run the program and showed you what kind of theories are consistent. And I want to point out there's really a very strong bottom-up constraint. So I only gave you the supergravity and anomaly arguments. There was no string theory involved here. But of course, 8D, n equals 1 supergravity, there's a lot of string theory constructions, and we heard that one of the best explored maybe is F theory on elliptically fibered K3. So you can ask the question, well, I found this anomaly constraint. Can I discover it in string theory as well? And it turns out that actually if you go to the mathematics literature, you will find that if you have elliptically fibered K3, where all of the Kodaira singularities that you have are of A type, so that's the SUN gauge groups, you get a geometrical condition. So if you're familiar with F theory, this has to do with the geometry of torsional sections. And it reads as follows. And you see that's precisely the same as here. So actually the anomaly constraints that you find in supergravity, just as like a consistency constraint of your gravitational theory, it's actually ingrained in the compactification geometry of F theory. Right, so I think that's very astonishing, meaning that we have a reinterpretation of some of these low energy consistency constraints in terms of a compactification geometry. Now, of course, as Miguel also mentioned, there's many string constructions of these theories. One of them has been investigated in very great detail and in the huge complete list of these models by many people here in heterotic string on T2 with Wilson lines, and you have to be careful. And there to find the gauge group, it's really about this lattice embedding into some string lattice that can be Narayan or CHL and whatnot. With Miriam Cvetic, Ling Lin, and Hao Shang, we did a similar construction where we don't do the heterotic string, but we construct, in principle, these lattices from string junctions in type 2B. So you really have this PQ branes, and then you can make sure that they have to end somewhere, and by this restriction that every PQ string has to end because you're in a compact geometry, you can find precisely the same embedding constraints, which is quite nice. So this is now, of course, a very strong top-down construction. So to summarize the first part, let me mention that anomalies are very powerful to constraints models from bottom up, and they can be matched from top down, and sometimes there is a beautiful relation between the two consistency conditions, right? So in particular, sometimes you can find the hints on what the geometry of the compactification should be. And I want to stress here that SUSY is not needed because I talked about anomalies, so those are topological. I don't care about SUSY, but of course, in the end, I do because the SUSY restricts the spectrum a lot. So I don't have to check everything, but I have a single 4-form in AD, right? So that is a lot of restriction entering there. And maybe as like it's like a motivation, I think if we now start including all generalized symmetries, also the gravitational sector, I think there is still a lot to be discovered in this area. Now, as always, even though this is very powerful, there's a flip side of the coin. Right? So maybe string theory is not as unique as we might think. So what do I mean by that? Well, think of a theory that actually has a very subtle type of anomaly, a discrete kind of anomaly. So that means there is no no real modification of the local degrees of freedom. It's very subtle, and we want to get rid of it. And there's various ways how we can get rid of it, so that we can, for example, try to embed some of the gauge groups in a larger group such that the anomaly vanishes. I can have some topological version of the Green-Schwarz mechanism, meaning that I don't include new dynamical degrees of freedom, only topological ones. So I don't modify the local dynamics. Or I can do a discrete modification of the fields I already have in the theory. So again, you wouldn't see it by local interactions, but only by subtle modifications. And in principle, how I cancel the anomaly is actually not unique. And that is precisely what my comment was for Severin's question. So turns out in type 2B string theory, duality symmetry in 10D, I'm talking in 10D here, the duality is anomalous. And you want to cancel this anomaly. But there's different versions. So we explored this in this paper with Jonathan, Arne, and Miguel. There's different versions how you can cancel this anomaly. Namely, for example, by this discrete modification of the Bianchi identity of the self-dual phi-form field. You can interpret this as the minimal version, because you don't include any new fields, not even discrete ones. But you can also include new topological sectors, right, of this BF type that, for example, have discrete higher form fields. And they can also do the job. And I don't know of any argument that either this or this should be forbidden. So if both of them are allowed, this leads to this picture that also was on Miguel's slides, where instead of this various asymptotic limits, you now also split these different limits according to the various UV completions associated to different topological sectors. Similar things happen in 6 dimensions. So in a paper with Paul Oehlmann and Thorsten Schimanek, we explored discrete gauge symmetries in 6D. So again, discrete gauge symmetries, they only have this very subtle anomalies, right? So this is the very discrete things that doesn't really change the local interactions. And you might ask the question, well, in 6D, usually if I ask a supergravity person, like, how do I classify my theory? Well, you tell me the number of tensor multiplets, you tell me the number of neutral hypers, or hypermultiplets, the charges, the vector multiplets. So here we have a model that only has the Z3 gauge, so there's no vector multiplet, right? It's not a dynamical degree of freedom. We have the same number of neutral hypers, we have the same number of charged hypers, and the same number of tensors, but different F-theory geometries. You know, it's like, okay, is this the same theory? And it turns out, no, it isn't, because the anomaly that appears in this Z3 is actually canceled in a different way. And that's precisely this discrete ambiguity that can happen in these kind of theories. And because in this case we rely on supersymmetry, or we have this supersymmetric model in terms of F-theory compactification, you can actually test this really by topological string partition function approaches. So you can test that the anomaly inflow on strings also for discrete theories, right, is different, and it's both is realized. And yeah, so let me give you the second lesson that you should take home. So anomalies and the cancellation, they're very powerful, but they also have this room for ambiguities sometimes. And of course, you can ask the question now, are some of them forbidden? If yes, why? So this would lead to some discrete swampland constraints, and these discrete swampland constraints are often very, very tricky. So it's like with the regravity conjecture and the sublattice, you can often make this, or there's no good argument excluding that you make the sublattice arbitrarily large, right? And this has to do with some discrete data. Can we make progress there? Or if they're allowed, do we really face now the issue of a string landscape that has this discrete possibilities? Both of them are exciting. Okay, so as a summary, let me just flash these 2 lessons you should learn. And let me mention that, of course, we now spend a lot of time in the landscape and deconstructing and constructing the landscape in Landscapia. But you should be very careful, because if you're in the landscape, the swamp thing is never very far from you. And in fact, it's true for Landscapia, because Swamplandia is also not very far from you. And so it's a pleasure to announce that it will happen in this beautiful place, as you can say, very dangerous, right? There's the landscape, and you're basically surrounded by the swampland in this monastery Seon, close to Munich, end of May, back to strings and geometry. So if you want to travel a little bit in Germany, this is a great opportunity, I would say, to attend both of these conferences. And with that, I end my talk. And of course, feel free to ask questions. Thank you very much.
Right, Marcus, thanks a lot for the very nice talk. Questions? Yeah, there's you there. Timo was first, I think.
The 60 example with the Z3, with the same Marsal spectra, how exactly do the F-theory geometries differ? Can you remind me?
So I can tell you from the field theory side, what differs is how the anomalies on the strings coupling to the tensor multiplet and the gravity multiplet. In one case, so there you have three possibilities. 0 is not allowed because you need some anomaly inflow in order to make this work. And then you have 1 and 2, right? And these are precisely how these models differ. So they have the same spectrum, they cancel the same anomaly, but you can cancel them in two different ways, which you can extract from the anomaly inflow onto the strings in this model. And that is different.
But what's the geometry?
Same
manifold? Different
No, it's a different manifold. It's a different manifold. I can tell
different
you.
Different while or what?
I think I have to check the table. Probably it's the Euler number. That might be but it's no, the neutral hypers are the same. So I can check the table, but we have this list.
There was a question here first. Here, yeah. And then.
So you said that one way of curing the type 2b duality anomalies would be to modify the Bianchi of F5 by some discrete terms. Could you be more specific?
Yeah, I could. So, right. So the duality is SL to Z or some refinement thereof, like MP to Z, and there is a way to decompose it into a Z3 and a Z4. So this is amalgamation is the phrase, right? So there's a nice way to encode the duality bundle in a Z3 bundle and a Z4 bundle. And this topological term will precisely be a cup product of the characteristic classes of this discrete gauge bundle. So these are classified by H1 of BZ3, BZ4. So this gives you the characteristic classes like the Chern class for U1. But they're discrete, right? They are only Z3, Z4, Z9, Z3 or Z4 valued, and you cup them and include them in there. So there is really no modification for any continuous variation, but only this very discrete thing, which makes it so hard to detect, and that's why it hasn't been in any calculation.
One last question.
Just my absence of knowledge of Calabi-Yau force. So when you compactify, for example, M theory and Calabi-Yau 4, you get some anomaly, which is the Euler characteristic divided by 24. Are all the possible Calabi-Yau force having an Euler characteristic which is a multiple of 24, or what you're saying is that you cannot compactify unless.
So So there is some restrictions. So Calabi-Yaus as spin manifolds usually have a coarse-grained integration, for example, of the second Pontryagin class, and the same here, right? So for example, if you restrict to spin manifolds, so these are usually classified in this deformation classes. In 4 dimensions, spin manifolds are generated by K3. That has the lowest number, which is the 1 over 48 P1 is equal to 1. But of course, we know that we can take type 2b and put it on a CP2, right? Which is not spin, but we can compensate in F theory by putting some non-trivial duality bundle, and then you can get around these consistency constraints. And a similar story I could imagine happens for Calabi-Yau 4.
All right. Then if there are no further questions, now we will go for the coffee break, and then we have a talk and another discussion session. So let's try to reconvene here in about 20 minutes or so. But first, let's thank Marcus again.
Thank you very much. Let's turn this on.
Okay, good. So where should I put it? Here?
Yeah. Now you're already on the speakers.
Oh, okay, good.
Okay.
Yes, good.
Nothing else?
I think so. Yes.
Want some water?
It's okay. I just had some. Thank you. Oh, hey.
You want to turn off the microphone?
Oh, how do I turn it? Turn down.
That's okay. Don't worry about it.
Yes. Now? Does it work? Okay, good.
All right, so welcome everyone to the last session of the morning. So to begin with, we have Peng Cheng talking about supersymmetric string vacuum with flat backgrounds. So please, Peng, go ahead.
Thank you, Ivor. So first I want to thank the organizers for this invitation. And today I want to discuss a little bit about the effect of flat background on constructing supersymmetric string vacuum. And this is going to be based on collaborations with Ilarion and Ruben. And because I don't know how to organize the topic, so I decided to, purely discuss about the examples in this talk. So the first example is discrete torsion. First, let's review some basic generalities of two-dimensional conformal field theory. We know that perturbative string theory is formulated on two-dimensional CFTs, and the Hilbert-Sweat carrier module over this via thorough algebra. And if I have a CFT and I have a normal symmetry, I could get it to formulate an RB4 CFT. And the Hilbert-Sweat structure of RB4 CFT will consist of several sectors labeled by the group element of RB4 group. And in each sector, we need to select out the neutral state under this RB4 group action. And the Protein function can be easily written down in this way, and it consists of several blocks with G, H, and G, H belong labeled by the group element of this RB4 group G. Here is perhaps the easiest RB4 CFT example. We consider compact boson with target space a circle of radius R, and then we have a Z2 symmetry, which corresponds to the half circle shift. If we get this symmetry, we see that this Z2 action will act on the momentum number and pick up a non-trivial prefactor. And as a result, the projected states will be carrying even momentum modes. And the twisted sector will give us half integer winding number and instead of integer winding number. And overall, of course, this is compact boson CFT with target space, a circle with radius R over 2. And then we see that from the construction, there is a natural generalization of construct RB4 CFT, which is first proposed by Waffa, and it's just introduced some non-trivial weights to each block. And after this generalization, we know that modular invariance will impose non-trivial conditions about these weights. And these are the two conditions imposed by modular invariance. And Waffa also proposed a family of natural solutions to it, parameterized by the second group cohomology of this RB4 group. And this set of solutions will be called discrete torsion. And here is an example of discrete torsion. We consider bosonic CFT with target space circle times circle. We could view this CFT as an RB4 CFT by gauging the Z times Z symmetry of R times R, two dimension of R times R bosonic CFT. And then we see that we have a family of discrete torsion given by the second group cohomology of Z times Z. And this is exactly the same as the B field moduli branch associated with this bosonic CFT. So from this example, we see that the flat B field background sometimes could be viewed as discrete torsion. Okay, now we can set up our example. I'm going to talk about 5-dimensional flat cipher manifold. And for simplicity, I'm just going to discuss one specific type of them, which is the 2 quotient or T5. First, we have 5 copies of circle. And there are 2 action X on the first circle. There are 2 action X on the first or fourth circle as reflection, and X on the 5th circle as half circle shift. And it is exactly because this shift that makes the entire geometry smooth. And we will call the 5th circle the cipher circle. And there are 2 ways of looking at it. Either we locate it as T4 fibered over a circle. When you move one loop around, it picks up involution, or you can view it as an ordinary cipher manifold. You view it as a cipher circle fibered over RB4. And from this description of its geometry, we easily see that if we formulate type 2A theory on this manifold, we are going to get 5-dimensional supersymmetric theory with 16 supercharges. And here the cipher circle is very important to the geometry of it. It is the cipher circle that makes the geometry smooth. So the question is, how does T-duality go with this circle? Well, first, let's switch to the CFT perspective. Focus on cipher circle. We know that the cipher set 2 will act on the relevant quantum numbers in the following way. It acts on the momentum mode and picks up non-trivial prefactor. And after T-duality, we see that the T-dual version with their 2 actions should act on the winding number and picks up a similar prefactor here. And we can also, and now we can also switch to the, we can also switch to the space-time perspective. Now we consider X5 as cipher circle fibered over RB4. We first compactify on the circle. What we are going to see is that we get a 4-dimensional RB4 together with non-trivial GU5 holonomy around each singularity, thanks to the half-circle shift of the cipher manifold. And then if we T-dual the cipher circle, we know that it's going to exchange GU5 and BU5. And if we start with T4 mod Z2, together with non-trivial GU5 and trivial BU5, T-dual will give us trivial GU5 and non-trivial BU5. And thanks to the trivial GU5, we see that type 2B geometry is singular. T4 mod Z2 times circle, but with non-trivial B-field holonomy around each singular locus. And although the type 2B geometry is singular, but from the dual 2A analysis, we know that all the singularities shouldn't contribute to the Maslow's modes at the generic radial circle. So there must be a mechanism involved with this B-field that makes all the twisted sectors massive. So the question is that what is the CFT associated with the flat B-field background? Well, the answer is discrete torsion. Conformal field theory with target space T4 mod Z2 times the circle could also be viewed as getting the symmetry Z2 times Z of the T4 mod times R CFT. And this time we see that we have a non-trivial discrete torsion. And we have this choice of turning on it, and this discrete torsion is given by this formula. It is very easy to check with the help of this discrete torsion. We find that in the type 2B, we just following the RB4 construction. It's very easy, just include this, I think just include this declaration. And then what you are going to see that it gives exactly the same spectrum as you expected from type 2A side. For example, in the untwisted Z2 sector, we see that the action will act on the winding number and gives the non-trivial prefactor. And also in all the twisted sector, you can easily see that you can pin down the entire perturbative sector of string spectrum, and you can see that they are all massive, although they are associated with space-time singularity. So the conclusion is that with non-trivial discrete torsion turned on, the twisted sector associated with spacetime singular locus become massive. And with the non-trivial B field around each singularity, we see that the singular locus doesn't enter into the low energy spectrum. And sometimes singularity doesn't enter into low energy spectrum is called fusion of singularity. And in these two papers, they've discussed one specific mechanism of fusion singularity by turning on non-trivial C1 holonomy around each fixed point. And the one we just talked about could be considered as a perturbative mechanism of fusion singularity, and it is related to their mechanism via string duality. To see that, first we put M theory on cipher times the trivial circle. If we first compactify on cipher circle and T-do the trivial circle, we're going to end up with 2B on this geometry together with C2 holonomy around the singular locus. But if we first compactify on circle and then T-do the cipher circle, what we are going to have is we are going to end up with exactly the same geometry, but this time with non-trivial B field holonomy around the singularity. And now the connection becomes extremely clear. These two backgrounds are related to each other by the SL2Z duality in type 2B. Okay, let's go to a second example, which is perturbative analysis of F theory on FHSV. FHSV is a very special Calabi-Yau threefold, which I'm going to review later. So first, SL2Z and F theory. Type 2B is believed to have SL2Z symmetry, under which in SAS are two forms and axion dilaton charges in the following way. And F theory is a theory makes full advantage of this duality group. And it typically provides supersymmetric string vector with axion dilaton vary along space-time, which makes it typically non-perturbative. But however, if all the monodromy involved will be just the central element of this duality group, then we see that axion dilaton is not acted upon by it. As a result, we can see that there is a hope of making the string coupling small universally along space-time, and the perturbative description should be possible. And this is indeed the case, and I think the first example was provided by Sen. First, we go to a specific moduli. First, we go to a specific point of this Abifold moduli, and we see that it admits an elliptic fibration, which is T2 fibered over T2 mod 2, which is P1. And then the monodromy involved will be just a central element of this SL2Z duality. And the perturbative description of it will be just Abifolding the type 2B worldsheet by the following Abifold action. I is referring to the involution on T2. Omega is the worldsheet parity transformation. And FL here is the corresponding to the space-time fermion come from the left moving sector. Okay, now we go to the FHSV. FHSV is a manifold first introduced into physics literature by Ferrara, Harvey, Strominger, and Waffa. And it's a small elliptic Calabi-Yau threefold given by taking a special Z2 quotient of K3 times T2. And the Z2 acts on the T2 as involution, and it acts on K3 is 6.3, and it projects out the top holomorphic form, which means that it acts on the integral cohomology, middle integral cohomology of K3 in the following way. It acts on the first gamma 1, 1 as involution, and it swaps the two gamma 1, 9. And as for the holomorphic structure, we see that it preserves the Kähler form and projects out the top holomorphic form. Of course, Emmerich action only exists on special locus of K3 moduli space. And here are some general features of FHSV. First, the action on the elliptic fiber is just an involution, which means that a perturbative description could be possible for this typical F-theory vacuum. And second, the Emmerich surface is smooth because the action is 6.3, and it doesn't emit a spin structure, simply because the two actions project out the top holomorphic form. So what is the worldsheet theory for this specific background? To answer this question, we simply need to find the worldsheet action X corresponding to the central element of this duality group, together with the worldsheet action corresponding to the space-time Emmerich involution. So here are some hints. First, in an SNSR sector, it gives space-time bosonic field, which means that these two actions should square to identity in these sectors. And in the SRNS sector, they give space-time fermions, which means that these two operations should square to minus identity. One way to see that is simply because this Z2 action, this Z2 Emmerich involution projects out the spin structure. And the Emmerich action, sigma, acts on the worldsheet should give the space-time Emmerich involution, which means that it should act on the chiral primary operators in the same way as it acts on the cohomology of K3. And okay, as for the action X, first, this field content should be charged under X in the following way. And also remember that according to the construction of FHSV, if we move one loop around, one non-trivial loop around Enric, B2 goes to minus B2, symbolically suggests that X should involve the worldsheet parity transformation. Combination of X and sigma is the two action that we are looking for. First, the action X. The requirement that the field content charged under X in the following way, together with the fact that it should involve worldsheet parity, uniquely fixes this action X. It consists of two components that both entered already in instance construction. FL, again, is referring to the space-time formula number, come from left-moving sector. It's also easy to construct sigma. For this, just recall some basic properties of K3 SFT. Okay, first we focus on in the NS sector. The relevant chiral primary operators are the following: the vacuum, which corresponds to identity operator, and we also have 20 quartets. They are in one-to-one oh, sorry. H here is conformal dimension. I is referring to the quantum number under SU2R symmetry. And they are in one-to-one correspondence with the 20 harmonic 1,1 form on K3. And they're further split into one self-dual quartet, where is the Keller class, and 19 anti-self-dual quartets. Also, the action on the chiral primary operators can be read out just based on the Enric action on the cohomology of K3. As for the other three sectors, they could be obtained by spectral flow operators. And if we select out the 2,2 super-conformal algebra out of the 4,4 one, we see that it has a property that the charge difference, the U1 are charge difference between the left moving and right moving satisfy the following property. The charge difference is an even number in the NS-NS-R sector, and it's an odd number in the NS-R-RNS sector. And based on all these properties, we can easily pin down the structure of this action sigma. The important piece is the important part is the first one, and the second one will act on the 4,4 super-conformal characters. And it is the first one that breaks 4,4 to 2,2. Or space-time, from space-time perspective, it is this part that breaks the hyperkähler to Kähler. And we can see that with this, we can see that sigma is indeed the two action we are looking for. It has all the required properties. The square to identity in the NS-NS-R sector, thanks to the charge difference is an even number, and the square to -1 in the NS-R-RNS sector. Now we have pinned down the Z2 action on the worksheet. All we need to do is just arbitrate it and apply standard worksheet analysis. Here are the key results. First, you see that half of space-time supersymmetry projected out. Space-time supersymmetry is 6-dimensional 1,0. And the vacuum is going to give a 1,0 gravity and 1,0 hypermultiplet. Self-dual quartet give a 1,0 hypermultiplet, and 19 anti-self-dual quartet give 9 tensors and 10 hypers. Matches perfectly with F-theory analysis. We can actually also go a little bit further by putting the theory on a circle and TDO it to 2A. This time the space-time internal manifold is going to be formulated on K3 times S1 mod Z2. And the only subtlety here is just that worldsheet parity needs to be replaced by the combination of worldsheet parity and circle reflection to be compatible with a symmetric GSO projection used in 2A. And the Z2 acts on K3 times the circle in the following way. It acts on X as Enric involution, and it acts on the circle as reflection. So as a result, we see that the internal manifold is going to be a smooth or orientable P- manifold, and the above construction just provide a type 2A perturbative supersymmetric vacuum without any extended BPS objects, and formulated on this unorientable P- manifold. And okay, so the topological condition for P+ and P- structure is the same as the topological condition for orientability and spin structure. It just requires certain combination of Stiefel-Whitney class to vanish. For example, for the P- structure, oh, this should be P+. Sorry. Oh, yeah, it's P+. Good. For P+ structure, we see that it should be second Stiefel-Whitney class to vanish. And for P- structure, it requires the following combination of Stiefel-Whitney class vanishes. Okay, up to so far, I only discussed about physics from the worksheet. Now I want to discuss a little bit about the M theory, which means that I have to switch my perspective from worksheet to space-time geometry. Okay, first, more about FHSV. I think the most striking feature makes FHSV so special is that it is mirror to itself. And there is no worksheet instanton correction to the Kähler module space in 2A, compactified on FHSV. One way to realize it is simply because the hyper-Kähler structure is only softly broken in FHSV. And one evidence for the self-mirror property is the following. I mean, this is not a very convincing evidence for the self-mirror property, but it's going to be relevant for our following discussion. So the torsion subgroup of K0 and K1 on FHSV are isomorphic to each other. And also, according to work by Greg Moore and Edward Wheaton, we know that the torsion subgroup of K0 and K1 classifies torsion flat Ramond-Ramond background in type 2A and type 2B. At the same time, they also classify the torsionful difference in type 2A and 2B and type 2A. And in type 2A, the flat R background classified by the torsion subgroup of K0 are generated by the 3 distinct C1 and 1 distinct C3. Sorry, I should replace it by G2 and G4, but it's torsion, so at differential form level, they're all 0. And more interestingly, in this paper, they observed, I think it's written by Yuka Brunner, Jacques Disteler, and Rahul Mihajan, I think. They observed that with certain flat C1 turned on, not all the torsional difference labeled given by the torsion subgroup of K1 are allowed to exist in spectrum. The argument goes as follows. In a specific point of the module space with gravity decoupled, type 2A formulated on FHSV will give us the 4D equals 2 theory with gauge group SU2. And the fact that 2A on FHSV receives no worksheet instanton correction, the space-time implication of that is this 4D equals 2 gauge theory receives no instanton corrections. As a result, it has to be finite. The only choice is SU2 with 4 flavors. And by analyzing the Messler spectrum in this limit, what they observed is that only when certain torsion D-brands are excluded from the spectrum can this theory be finite. Otherwise, it will give 8 fundamental flavors, which signals the inconsistency of string theory itself. The self-consistency of string theory requires absence of some torsionful D-brands. In the last page, I want to provide an M-theory perspective to justify the observation made in Yuka and her collaborators' paper. First, we realize that instead of K-theory, the C3 field in M-theory seems to be classified by equivariant or differential refined version of integral cohomology. And from M-theory perspective, with the presence of the torsion flat C1 will uniquely fix the M-theory 7-dimensional manifold, which is a circle fibered over FHSV, with a circle fibration characterized by this flat C1 background. As a result, once we have fixed the 7-dimensional geometry according to this C1 in type 2A, we can carefully study the lift of K-theory class C3 plus C1 in M-theory picture. And what we found is that if we analyze the M-theory flat moduli space, we see that the K-theory class given by C3 plus C1 is actually identical or connected to the K-theory class with trivial C3, which means that M-theory analysis simply suggests that type 2A module branch labeled by 2 distinct K-theory classes are actually connected. Combined with this fact, together with the perfect pairing between torsion D branch and torsion R fluxes, we see that, at least at the torsion level, it seems that the K3 and you shouldn't be able to detect any differences between the K-theory class labeled by C1 and C1 plus C3. And as a result, they simply impose a condition on the torsion D branch, which satisfies the following property. And it is exactly this property that gives you exactly the same physical D branch that already been observed in the paper that to satisfy the self-consistency of string theory itself. And of course, this example leads to lots of problems. For example, what is the right way to characterize a module of flat background? And how to reconcile the fact that the flat background in type 2A and in M-theory are actually classified by 2 different cohomology theories. And these problems are currently under our investigation. Thank you very much.
Right, thank you. All right. Okay, now it's what? Question.
Thanks for the nice talk. I wanted to ask about the last piece. So will you have this consistency condition on the alpha on the torsion D brains?
Yes.
what's the M-theory interpretation? Is that they're wrapping something which is actually trivial in homology, and then they can unwrap, but you don't see that on the base, or?
You mean what is this one?
Yeah. That condition can be interpreted just geometrically in M-theory?
Yes. You
It's
mean
just
that
that
what's the physical condition counterpart to this one? This is purely some algebraic topology.
Can you say?
Your question is what is the physical
Yes.
problem?
Yeah.
Well, I mean, this is very subtle, because if you apply, you see that Frieda-Witten anomaly already vanishes in this case. So it's, I mean, even Frieda-Witten anomaly, it doesn't help. So this case, I don't know, at least for the physics. It's not clear.
But I was asking, is the picture that the torsion deep branes that are wrapped in those cycles are actually unstable and can be unwrapped, or is just inconsistent to have those deep branes?
No, it's not. I mean, I hope it's inconsistent. But
You think it's inconsistent? Okay.
But I'm not sure, because the only inconsistency condition is Frieda-Witten anomaly, but it satisfies the cancellation of Frieda-Witten anomaly. So.
Okay, thank you.
Over there.
Hi, thanks for the nice talk. My question is also on this slide. Are these circle fibrations over the FHSV manifolds? Is this one of Joyce's G2s?
No.
No. Okay. I see. All right. So I guess it'd be like a new one per se, or
a U1? Yes, a U1, just a U1.
Oh, no. I said a new G2, I guess.
This is the holonomy is SU3, still SU3. The circle is flat.
Oh, I see. Okay. All right. Sure. And so the statement of the C3 being possibly classified by ecovariant integral homology. So one sort of like thing pointed out by like triples, fluxes, and strings is that, you know, if you have like these frozen singularities, like in some sense, the C3 is like almost like a subset of the ecovariant.
Also they proposed one consistency condition about this deep branes together with this Raman fluxes, but that one is too strong. It's not the right one.
Sure, I see.
For example, in this analysis, if you impose their condition, what you are going to end up with 4 adjoint flavors. It's again signal the inconsistency of string theory itself. So that one is too strong.
Okay. Thanks.
Any further questions? Looks like there are no any further urgent questions. So then let's thank Peng again.
Thank you.
And now we will have our discussion session on string universality and classification of string vacua. Just a quick clarification about the discussion. So the idea is that everyone can interact and so on. And for that reason, we are trying to avoid using the mics for the audience during the discussion. So if you guys can speak up, we would very much appreciate it.